Good. Ya está. Bueno, ahora sí, después de toda esta odisea tecnológica, creo que podemos dar inicio al coloquio extraordinario del día de hoy. Bueno, el día de hoy es un placer tener a Joel Sánchez-Bermúdez. Él es postdoc en la ESO en Chile. Y ustedes lo recordarán quizás que hace unos meses nos volvió a visitar y nos dio también un coloquio. También Joel va a ser un nuevo integrante del instituto a partir del diciembre o algo así. Se va a integrar como nuevo investigador del instituto. Y el día de hoy nos viene a platicar sobre Science with Optical Infrared Interferometry from Sparse Aperture Masking to the VLTI. Por favor.
Okay, well, so first of all, thank you very much. It's again a pleasure for me to be here and to talk a little bit about the science that I do. And the idea of the colloquium is explain or to provide an overview of what science can we do with the VLTI. So optical interferometry has been a growing science for the last 2 decades, particularly because of infrastructures like the Very Large Telescope Interferometer, which is this complex of telescopes located in Cerro Paranal in Chile, but also because of other interferometers in the world, like, for example, CHARA in the United States, which is able to combine up to 6 different optical telescopes in order to make an interferometer. However, despite the importance of these new technologies, the community is still very small, because up to now it has been basically restricted to the countries that has been able to develop this new technology. But now, with the advent of new instrumentation in this kind of facilities, we try to open more the community, and obviously to attract more people to use the facilities of the VLTI. So the idea is more or less to, as I said, to provide an overview of the instruments that are deployed at the VLTI, and a little bit of the science that has been done during the past years and what can we do. And if you are interested, of course, in doing something with this kind of instrumentation, then we can discuss and see if we can, for example, to make an observational proposal to observe something in the next call for proposals in September. So, as I say, optical interferometry is a relatively new technique. Well, it's the technology to perform optical interferometric observations or infrared interferometric observations is relatively new. However, the idea behind interferometry is not so new. No, it was developed first during the 17th centuries when Christian Huygens described the wave nature of light, and then, of course, the famous experiment of Thomas Young, in which described the interference, which is the phenomena in which the interferometry, or the nowadays interferometry is based, optical, infrared, and radio, of course. And then, of course, Fizeau developed suggesting that interferometry could be used in astronomy to measure the sizes of several stars. And, of course, Michelson describing the concept of visibility, which is the observable that we have with our interferometers. So the experiment, or the idea in which an interferometer is based, is basically the Young experiment. No? If you have a source of light, and the source of light passed through a couple of slits, then each of these slits become a new source of light. And if we have a screen here in which we could record the interference pattern of this of the light that passed through the 2 slits, we will see a fringe pattern like the one that we see here. So in fact, it is not so difficult to reproduce this experiment. You just need to create, or for example, you can use a piece of aluminum and then do a couple of pinholes separated by 1 millimeter, and then you could observe, for example, the light bulbs of the street, and then you will see the interference pattern produced by your interferometer, like, for example, here. Of course, depending on the distance and depending on the size of the light bulbs, you will see different patterns here. So interferometers basically measure the properties of the fringes that we record in a detector. No? And this the size or the contrast of these fringes is what we call the visibility. And visibility is nothing else but the contrast between the maximum and the minimum of the fringe pattern that we have here. And depending on the size of the source, in the direction across the two slits or the two pinholes of our interferometer or telescopes, we will see different contrast. And this contrast and the measurement of this contrast tells us information about the angular size of the source that we are observing. Of course, there is a mathematical theory behind this, which is expressed with the Bands-Iter-Zernike theorem, which basically says that the spatial coherence function is linked through the Fourier transform to the angular intensity distribution of the source, the brightness distribution of the source projected in the plane of the sky in the case of an astronomical source, plus or convolved with the transfer function of our interferometer. So interferometry has been in astronomy for the last 40 years, perhaps more, and it has been quite or extensively used in radio. No? We have these huge facilities like the BLA or ALMA that can combine, well, not hundreds, but tens of antennas, and then to produce images, high-quality images of the sources that they are observing. However, in the optical or in the infrared, it has been more difficult, and it's basically because there are several technological limitations or several, the main problem with the optical or infrared is basically the technology that we need in order to perform interferometric observations. So, for example, in the case of the VLTI, up to now, we have only been able to combine up to 4 telescopes, not more than 4 telescopes, while in radio you have, I don't know, with ALMA is more than 60 antennas, not 60-something antennas. Of course, there are other differences, like, for example, the scale of the wavelengths. No? We are tracing wavelengths that are much more smaller than in radio. The properties of radiation, there are some quantum effects involved here. And of course, the atmosphere plays a major role in the way we perform interferometry in the infrared. By the way, the VLTI works at infrared wavelengths. So it works in H-band, 1.76 micrometers, K-band, 2.2 micrometers, more or less, the central wavelength, and also in the mid-infrared, no? L-band, M-band, N-band. So from 3 micrometers up to 12 micrometers, more or less. But we call it optical interferometry because the elements that we use in order to perform or to record the fringes are basically optical elements. So we use mirrors, we use glasses, and we use waveguides in order to create the light path before the combinations in the beam before the combination of the light at the beam combiners or the instruments. So that is why it is called optical, not because so the term optical is referring particularly to the elements used to combine the light, not to the wavelength of the light that we are observing. So this is exactly what I was telling you before. Visibilities are complex quantities, and this is the theorem that I mentioned before, and it basically tells us that the measurement that we got in our interferometer is nothing else than the Fourier transform of the brightness distribution of our source convolved with the instrumental transfer function. But there are differences between infrared and radio for the observables that we are trying to measure with our interferometers. In radio, people usually measure the visibility amplitude, so the amplitude of the fringes, and the phases of the fringes. While in the optical, we use the square visibilities, and we use a quantity called closure phase. And we use this quantity called closure phase simply because the atmosphere plays a major role in the way we record the signal. There are some other quantum effects that I already mentioned before, and the idea is that there is this quantity here called the mean occupation number, which basically tells us the number of photons per wave of radiation that we are measuring for a given source of a given temperature and frequency or wavelength. And for example, in radio at 2 centimeters, if we are observing a source with mean temperature of 5,000 kelvins, then the number of photons in an integration time is around 7,000 photons. No? So we have enough signal. But in the infrared at 2 micrometers, if we try to measure a temperature at the sublimation point of the dust, for example, we have less than 1 photon. So the instantaneous signal-to-noise per integration time is less than 1 in the infrared. And that's why we cannot use the instantaneous fringe amplitude in our interferometer, and we have to use a mean measurement of the fringe. So we use the square visibility, which is basically the mean power encoded in the fringe. Also, of course, the photon noise follows a Poisson statistics that is different from the Gaussian statistics. And this is why we use the closure phases. So imagine that we have 3 different telescopes, and above each one of these telescopes, we have the atmosphere. And the atmosphere is inducing these phases in the signal that we are recovering. No, it is creating this turbulence, and the turbulence depends only on each one, or is different depending on each one on the different stations that we are having here. So in order to eliminate this atmospheric term in the phase information that we are recovering, we perform the product of 3 different baselines in a closed triangle. The product of 3 different baselines in a closed triangle, and by performing this product of baselines, we basically can cancel this atmospheric term and then end up with a phase information that depends only on the brightness distribution of the source. However, this induces some effects if we want to recover images, because we don't have a one-to-one correspondence between the amplitude of the fringes and the phase information. So this is a problem because, for example, in radio, you measure your fringes, you measure your amplitude and phases, and then you just perform a Fourier inversion. You use clean, and then you can recover images. While in the optical or in the infrared, it's not the same, and we have to use another methods in order to do the imaging. So imaging at infrared interferometer is nothing else than a regularized minimization. We have to regularize. We have to minimize the likelihood, so the difference between a model image and the data that we are getting, plus a regularization function that we introduce, and it includes some a priori information of the brightness distribution of the source that we are observing. So again, during the last 10 years, there have been several softwares developed in the community to perform this minimization. However, this is still a field under development, and it's going to be very, very important in the next year to perform or to create software in order to perform these kind of minimizations, particularly due to the new instrumentation, in this case at the VLTI. So up to now, to keep in mind, so optical infrared interferometry have some important differences with radio, particularly in the way we measure the phase and how we recover the images. The atmosphere plays a major role, so that's why we cannot do simple Fourier inversion like in radio. We don't measure the amplitude and phase directly on the coherence function. Well, the observables are different, so we use the B-square and the closure phases. And the closure phases tell us information about the point-like symmetry of the source. That's why we are measuring there. So this is the Very Large Telescope Interferometer. As I said, this is a complex of telescopes located in Cerro Paranal in Chile. So, and we can combine up to now 4 of these telescopes. Either we can combine the 4 8-meter telescopes called UTs, or we can combine up to 4 small telescopes called ATs. These small telescopes have a diameter, the primary mirror has a diameter of around 1.8 meters, and these are movable telescopes. So we can change the location of the stations, and then we can get different UV coverage of different interferometric arrays for our observations. The maximum baseline here is 130 meters. There is one station here that reach up to 140 meters, 140 something. And these, for example, in K-band at 2.2 microns in the near infrared provide us an angular resolution of 2 milliards seconds, more or less. So these are some of the characteristics. This is again the platform. Here we have the UTs, and here we have the different stations for the ATs that we can combine depending on the necessity of our science. So we have maximum baseline 140 meters, minimum 111 meters, and then there are 3 different instruments that can be used by the community now. Gravity, that works in K-band, again 2.2 microns. Pioneer, that works in H-band, 1.7678 micrometers. And then Matisse, that was deployed just a couple of months ago or 3 months ago, that works in the mid-infrared from the L band to the M band. So Pioneer was a visitor instrument deployed in Paranal in October 2010. This is the optical table in which the instrument is located. It was the first instrument that allows the combination of 2 to 4 telescopes, and it was developed by the Institute of Astrophysics de Grenoble, and it was developed to study different evolutionary states of planet-forming environments, but also multiplicity in massive stars and so on. It has similar baselines to the predecessor called AMBER, and it works in the H band with no spectral information. So it's basically just 5 channels across the H band, so we cannot perform spectro-interferometric observations with this instrument. We have to observe science and then a calibrator, which is basically a point-like source of more or less the same brightness, located not so far away from the target, in order to calibrate the the instrumental transfer function and the atmospheric transfer function of our visibility. And this is the sensitivity limit in H-band, 7.5. This will increase, particularly at the end of this year, because there is going to be a new adaptive optic system for the 1.8 meter telescopes. This new adaptive optic system is called Naomi, and the idea is to reach a magnitude of 9 in H-band with Pioneer, with this new AO facility. Some examples of the science that has been done with Pioneer. So, for example, is in this paper published by Sana and collaborators in 2014. It's a paper dedicated to study multiplicity in massive stars. So, you know, massive stars normally or usually come in multiple systems. It could be binaries or high-degree multiple systems. And, of course, characterize this, the degree of multiplicity tells us information about the mechanisms that form those systems. And, of course, about the formation and evolution of massive stars, in this case, O stars. So, for example, in this paper, they analyze up to 96 O stars with different techniques: adaptive optics imaging, classical imaging, spectroscopy, and also interferometry. And interferometry covered this gap. So we have the angular separation here, and we have the delta magnitude here. And, for example, if you use an infrared camera like NACO in an 8-meter telescopes, you can cover this angular separation. If we use a special Fizeau interferometric technique also in an infrared camera that I will explain later, called Sparse Aperture Masking, you could cover then this range of separations. Here, if you have the spectroscopic data, you can cover angular separations smaller than 1 milliards seconds, for example. And then Pioneer or infrared interferometry cover this part here. And then we could have, by the combination of the different techniques, and a statistical overview of multiplicity in this kind of object. So the conclusion for this paper was that more than or 90% of the massive stars, of the O stars analyzed here, have at least one companion. So, for example, Pioneer was also very good at allowing us to perform images or to reconstruct images for the first time using this kind of observations. Before Pioneer, particularly for AMBER or MIDI, which were the 2 previous instruments at the VLTI, people normally observe the sources, they recover the visibility, they recover phases sometimes, and then they model this visibility and phases in the Fourier space using a model of a disk, a model of a binary, a model of a halo or a ring, etc. So these geometrical models, sometimes some radiative transfer models, but all the information were done in the Fourier space. So with Pioneer, we had the ability that for the first time to recover images with complex structure at milliard second resolution in the H bands. For example, this source here, this Amira star called ERCAR, that these data were so here you have the visibilities versus spatial frequencies, and you have here the phases versus spatial frequencies. As for example, just by looking at the phases, you will see that they vary between minus 180 degrees up to 180 degrees, which means that the source is asymmetric. And the idea is to recover these asymmetries with the images, because of course, doing a model of this in the Fourier space could be quite challenging, right? Particularly for the phase information, to recover the asymmetries here. So these data sets were real or are real, taken with Pioneer, and they were used for this interferometric imaging beauty contest, which is performed every 2 years and is presented at the SPI conference. In fact, today they will release the results for this year winners. And this, it was explained here in this paper by John Monnier in 2014. And this is, for example, the structure of RCAR mapped with Pioneer. And for example, we see here the photosphere of the source. We observe some blobs in this star, but we also observe some dust shell, what we believe that are some asymmetric dust shells around this Mira star. So for example, these kind of observations would be very useful if you want to study the dust, where the dust is formed in this kind of objects, or how the formation of dust or the production of dust is linked to the pulsation phases of the stars. No, this is the star. So the photosphere is here, and these are the. It could be some irregularities or convection cells in the stars. We still don't know that. So there are people that are trying to model this actually. So if they correspond to some, for example, yes, some convection cells for this kind of objects. But the idea is, so this is -5 to 10 milliards seconds inside, or 15 milliards seconds inside. So that's the resolution here is around 2 milliards seconds, or even a little bit less. So what we can gain with these kind of observations, which is, so it's really high angular resolution. For example, there is also this paper published by Lazarev and collaborators, just like here, in which they basically did a statistical measurement of the angular sizes and shapes of disks around Herbig stars. So here you have again the visibilities, the phases. You see how they variate. This is the UV coverage that they got for 2 different sources here, and these are, for example, the images that they recover of the brightness distribution of the disks around T Tauri stars. Now, for example, and again here is 4 milliards seconds, 5 milliards seconds inside, and here also. So these kind of observations of this kind of studies could be done or with Pioneer in the H band. Again, they can only produce images of the continuum because Pioneer does not have this spectral information, but still is quite useful if you try to model the different disk properties in this kind of objects. And since 2016, there is a new instrument at the VLTI, and this instrument has been a revolutionary one. So this instrument is called Gravity, and it was basically developed. So it was developed by the MPE in Garching, and this instrument, the primary goal of this instrument was to monitor the path of the S2 star, which is the closest star to Sagittarius A star, so the black hole in the center of our galaxy, and then to test the general relativistic effects in the passage of this star. So basically, and those measurements has been done during the past years. The campaign started in March, and it will continue up to August this year. But it's quite astonishing because it provides new technology. So this is Gravity, and these are some of the characteristics of this instrument. This works in the in the K band. This is the angular resolution. But the new things is that this instrument allows us to have phase reference visibilities, also narrow angle astrometry with this precision. This should be 10 microarc seconds. Simultaneous observations of 2 objects at the same time. 3 different spectral resolutions from 50 to 4,000, and the limiting magnitude is 16 in K band. And I'd like to highlight some of the technological developments of Gravity, like, for example, this infrared wavefront sensor called CHAOS, which is new because before the CHAOS of these Shakarman wavefront sensors, people only were the VLTI only has wavefront sensors in the visual, which makes more difficult the observations for embedded sources in the infrared. Also, the star separations that allow us to perform the dual field observation. So this idea of observing 2 stars simultaneously with the instrument, and of course the fact that the beam combiner is an integrated circuit. So it's a piece of silicate in which you carve some waveguides, and then you use these waveguides to redirect and combine the light that is basically recorded at the end in the detector. So just to provide you an overview of the complexity of this instrument, I will play a small movie. So you will see all the parts of gravity here. So it lasts like 4 minutes or something like that. So it'll be lower. So you have the star, the Earth. This again, the VLTI, the 4 telescopes. Here, this part here is the control building. So you will see all the reflections that need to be done in order to record the fringes for this instrument. So this part of the video is just to illustrate the reflections, to perform the adaptive optics correction. This is the part where the CHIAOs are. So these adaptive optics facilities in each one of the telescopes. In each one of the 8-meter telescopes, you have this, and here you perform the correction, no? Just to eliminate to compensate for the turbulence of the atmosphere here. And you have a Shakarman detector here, and then you compensate here the phases induced by the atmosphere. This part is just for that. And then here, so the CHIAOs, each one of the CHIAOs are located in the base of the telescopes. But then you also send part of the light through these tunnels here to the VLTI complex building, which is here. And at the basement of this building, you have gravity here. And then this is the light that goes inside the instrument. You have some internal delay lines. So these delay lines are basically to compensate the different paths, the different light paths of the telescopes in order to synchronize the signal, to say it. You have here the star separators. So if you are observing, for example, 2 objects at the same time, you have here the pupil as it's seen in the sky. And then, of course, again, you send portion of the light through the beam combiner, and the beam combiner is where you perform the interference of the light. So this part is in red because it is the light is so you pass the light through a monomode fiber of each one of the telescopes there. It's like a roller coaster. So finally, you arrive to the beam combiner there. So you have 4 entrances there for each one of the telescopes, and then here you have the waveguides. And these waveguides induce some phase shifts of the light in order to sample the fringe at 4 different positions. And then you end up with a fringe pattern here. And you see that this is a dispersion axis because, for example, you could go up to 4,000. You disperse the light with a prism of up to 4,000, not to have some spectral information there. So some of the science that has been done with gravity, well, gravity also has been used in order to measure multiplicity in known stars with high precision astrometric measurements. This was the astrometric measurement obtained for this particular target, obtained in science verification data, and you can basically see here quite clear the cosine function of the binary or the binary signature. And you have here, for example, this is a reconstructed image. You have the primary component here, the secondary component here, and some previous measurements with aperture masking and also with Pioneer. But the astrometry here was 10 to the minus 3 milliards seconds, more or less. We could also perform interferometric observations of the line emitting regions in the spectrum of the sources here. So you have your interference pattern, and here you have the dispersion axis or wavelength, and you basically measure the flux centroid displacement between the continuum and the position of a given line, for example, bracket gamma. And then this displacement is linked to the phase information that you have with your interferometer at a given baseline. And for example, for 120-meter baselines, for displacement of up to 15 degrees, you could get a precision, an astrometric precision of the displacement of this quantity here, 0.16 milliards seconds. And then performing these measurements at different position angles allow you to constrain some properties of the asymmetry of the line emitting region that you are analyzing there. This is also quite interesting. You could measure now multiplicity of tests, multiplicity in crowded fields, like for example in the center of NGC 3603, and use one or several sources as science targets while you are locking the fringes or sampling the fringes on one of the other objects. No? For example, here you could use this Wolf-Rayet star here in order to lock your fringes with your fringe tracker, right? To measure the position of your fringe, and then integrating one of the fainter objects here, like for example in one of these O stars, and then go to fainter sources up to 10 magnitudes in K-band, and of course observe or to perform fast sampling observations. Now, for example, 5 sources, you can test 5 sources in a couple of hours only, and in for example regions like this, and also the galactic center or other complex or other clusters. You could also study more complex objects, like for example pinwheel nebulas. So these pinwheel nebulas or these spirals are created by the rotation of a binary in the core of the system, and the dust produced by this binary. And of course, since the binary is rotating, it is creating this spiral structure around the source. In fact, these spirals were first imaged with aperture masking observations, also another interferometric technique. It was Peter Tothill, the one that first observe and create the images of these kind of objects. And now the idea with gravity could be to test where the dust is formed, because we have the resolution of the 2 milliards seconds again in order to see where exactly the dust is formed between the stars in the center of the system. Now, if the dust is formed in the win-win collision region, if it is at a given distance of this of the collision region, how the dust distribution is performed in the head of the spiral, if it is uniform or if it is clumpy. And so this is another of the ideas of the science that can be done with gravity. So I must say that I observed this target a couple of weeks ago, and we managed to recover fringes. It was quite difficult because the target is really resolved. So the amplitude of the visibilities is very, very small, but we managed to record fringes for this object here, particularly. And this is a movie of how it moves. For this source, I think the period is 500 days or something like that, 500, 600 days. So you could basically sample different orbital phases in a period of 1 year or 2 years. This is one of my favorite projects because we study eta car with gravity. This is the spectrum that we observe with gravity. So we have two really prominent lines, bracket gamma here, and this is one helium. This is a helium-1 line here, and this is just as an example the differential visibilities across the line compared to the continuum. So, for example, in the continuum, you clearly see that the structure in the line is different than in the continuum, and also you see that it is asymmetric because the phases variates here. And the idea of this project was to perform for the first time chromatic image reconstruction of the brightness distribution of the source across the line. So we were able to reproduce the bracket gamma line, but also the helium-1 line for the first time. And you see how as we move towards the line, the structure of the source becomes more asymmetric, and you have here this extended asymmetry. Sorry? No. So this is the okay. So technically, eta car is a binary system, and in fact, what we are observing here is the wing-wing collision zone of the binary. We cannot resolve the secondary because the secondary is quite faint still for this kind of observations, but we observe the effect of the wing-wing collision interaction, and this is this asymmetry that we observe here. And basically, because of the orientation of the system in the plane of the sky, that's why we are observing it towards this position angle. But this is just an example of what we can do now. No? So we can recover, this is again milliards seconds, and this is 10 milliards seconds in size. No? So with this, so let's say, for example, eta car is 2.3 kiloparsecs more or less. So this is 50 AU, something like that. The scale that we can measure. No, 5 AU. No. This is not this. This is the primary wind. So because in this case the primary is also quite embedded. So we cannot resolve the star. So what we observe is the primary wind. So what we say is the continuum is the primary wind, and as we move towards the line, we observe this effect because the secondary carves a cavity, and then we observe the emission coming towards the walls of the cavity. And because of the orientation, we observe this asymmetry for this particular position angle. So this, for example, for this object, there was a paper published before in 2016 by Gerd Weigel using amber data, so this predecessor of gravity, also the VLTI, observing the same star with a slightly smaller angular resolution. I think it was 6 milliards seconds or so. And then they found more or less the same, but only for bracket gamma. But with gravity, we were able also to recover the structure in the helium-1 line. And then there is MATISSE. So MATISSE is the other instrument that was, as I say, deployed 3 months ago at the VLTI. So it works in 3 different bands, L, M, and N. These are the resolutions that you got with the auxiliary telescopes, with the unit telescopes. And you have different spectral resolutions for the different bands. Now, if you observe the L and the M band simultaneously, you could get this resolution and so on. So you also observe you also have some spectral information of with this new instrument there. So what are the differences between MATISSE and its predecessor MIDI? So this was the previous instrument at the VLTI for mid-infrared wavelengths. And it's basically the fact that with MATISSE, we have absolute visibilities, we have chromatic differential phases, and we have closure phases. MIDI could only combine before 2 telescopes. And by combining only 2 telescopes, we could not do this closure phase, would not have these closure phase measurements. So people could not recover images at mid-infrared with this particular angular resolution. But now with MATISSE, it can be done. And then MATISSE is, for example, an excellent instrument if you want to study the dust distribution around T Tauris or Herbig stars or massive YSOs or also AGNs. No? And this is a model of this particular object. That this is a Herbig star, and you have, for example, a compact halo here, a rim here. And what I did was to do a simulation of 3 nights of observation with MATISSE, getting this UV coverage using the 80s at 3 different configurations and low resolution observations. And then these were the data these are the data that I simulate. Again, square visibilities versus spatial frequency. And here you have the closure phase versus spatial frequency for a relatively small signal to noise here in this case for this particular simulation. And then I managed to, or I tried to recover the brightness distribution of the source using different algorithms with different regularization methods, like, for example, the L0 norm, the entropy, the L2 norm, total variation. And with this simulated data, of course, including all the systematic effects that we expect for the capacities of the instrument and so on, we basically managed to recover relatively well the brightness distribution of this model. So, for example, in this case, total variation was the best one in order to recover the real brightness distribution. But again, as I mentioned before, there are still some differences between the different methods used here. for the image reconstruction. And this is a very open field, and it's very interesting, or it will become more important during the next year if we really want to recover high fidelity images with these kind of instruments and not being biased by the a priori knowledge that we put in the software to perform the reconstruction. And as I perform the simulation in low resolution, I also image channel by channel the simulated data. And for example, for these channels, I managed to recover the central source here, and then the central source disappear, and so on. So we more or less set up or establish a limit between the flux, or a limit in the flux ratio between the central source and the disk that could be recovered with this kind of simulations for this particular model. So below 2.3% in flux ratio, we cannot recover the central source, for example, with this particular simulation. And this is the other technique that I like a lot. It's called the Sparse Aperture Masking. This is Fizeau interferometry. And this was the first. So during my PhD, I used infrared interferometry to do my thesis. But this was the first technique that I learned to use. And it basically allows us to transform a single beam telescope, a single dish telescope, into an interferometer. And we do this just by placing a mask with several pinholes at the pupil plane of the telescope. So at the camera, what we recover is this interference pattern, which is produced by the geometry of the mask convolved with the brightness distribution of the source. So for example, for this particular mask, this is the UV coverage that we would get. And this is what we call the interferogram that we would get for a point-like source. But of course, this interferogram is modified depending on the brightness distribution of the object that we are observing. And you may say, well, why is this important? Why we want to cover the pupil of a telescope with a mask with some pinholes there? And then what can we gain with this technique? No? First of all, the resolution increases. So instead of having lambda over d, we have lambda over 2d. So for example, 35 milliseconds at 2 microns for a 9-meter telescope. We have a very well and stable PSF, right? This is a complementary technique to coronagraphy, and it's also important because with aperture masking we have inner or smaller inner working angles, and of course we can study the circumstellar material at these scales for several sources. So, for example, this is a study of the central parsec. So we have here. So this is the central parsec of our galaxy. And we have Sagittarius A star, which is the black hole. This is an imaging radio. And then you see that we have this arm of gas and dust that orbit the supermassive black hole in the center of the Milky Way. These spirals of gas and dust are called the mini spiral. And embedded into this mini spiral, there are some stars. Like, for example, these objects here, IRS-5, IRS-10 West, 1 West, 21, and so on. And these sources are not point-like sources, so they have some they have some structure that are produced by the shock of the winds of these stars and the interstellar medium, so the mini spiral, and also because of the motion of these stars through the mini spiral. So, for example, in this case, we use aperture masking. So this is the same field observed through the mask, and then you see the different interferograms depending on the different structure of the targets that we are observing. And then, for example, for these targets that are point-like objects, you observed a very or a crispy interferogram defined there. But for other targets that are more resolved, you observe a more blurry interferogram, like, for example, here or here. So we use, again, these algorithms to perform image reconstruction, and these are the circumstellar material that we observe around the different targets that we analyze. And for example, for IRAS-5 or IRAS-10 West, we clearly observe this bow shock morphology that we suspect is formed again by the motion of the star through the interstellar medium and the shock of the winds of these stars, which we suspect are well rayed with the interstellar medium again. And the idea, of course, was to use this model, these images, and then use a multi-wavelength imaging study. In this case, we complement them with classical AO observations. perform proper motion measurements over different epochs, radiative transfer modeling, and to finally determine the orbital parameters of these stars. It's important to obtain, for this particular case, it was important to obtain the orbital parameters of these objects because there is still a debate in the literature how massive stars were formed in the central parsec of the galaxy, and if they were formed, for example, in a very dense disk that was orbiting the supermassive black hole in an episode of with an age of around 6 million years ago or so. But this is still not so clear whether these stars belong to that disk or not. But for example, aperture masking could also serve as an spatial filter. And here we have a classical adaptive optics imaging, again, of the central parsec. I think this was simulated in the L-band, where you could observe more the diffused emission of the mini spiral there. And then once you use the aperture masking observations, you basically filter out all this extended emission. And then you only end up with the circumstellar emission for the angular scales covered with your smallest and largest baseline in your mask. And for example, in this case, you could perform more precise astrometric measurements of the different motion of the stars in this kind of fields, in crowded fields, like, for example, the central parsec. And just to see this example here, in this complex IRS 13, you don't distinguish here all the point-like sources embedded into this part of the field of view, while when you use the aperture masking observation, you could distinguish the different sources here more clearly, and then you could measure the astrometry or photometry of each one of those objects. So here I only illustrate some of the cases some of the scientific cases that you could study with optical interferometry. But of course, there are many other subjects that you could do. This is, for example, a distribution of the time used at the VLTI for different scientific topics. And I don't know, you can study pulsating stars, young stellar objects, dust shells, binary stars. You could do astrometry. Also, people now are beginning to study AGNs or also pulsars and things like that. So it's a very, I think it's a very interesting technique for the people that would like to do high angular resolution observations. And there are plenty of scientific cases in which you could exploit the facilities of this kind of technology. And just to keep in mind at the end, so VLTI has the best angular resolution in the infrared, near infrared and mid infrared. 3 instruments are there, 2 in the near infrared and 1 in the mid infrared. Now there is an improvement in the sensitivity and UV coverage, particularly with the new instrumentation. Pipelines and software are still under development, particularly for the image reconstruction. So if you are interested in that topic, it's also a good opportunity there. And it's a very useful facility to study stellar astrophysics and now AGNs also. And that's all from my side. Thank you very much.
Questions?
Es que había muchas preguntas, pero ya me fue. A ver, un par de preguntas. ¿Cómo cuánto tiempo le están dedicando en Paranal o donde sea que estén el VLT a trabajar interferometría? ¿Cuál es la fracción de tiempo que le han dedicado históricamente en los últimos 3 años o lo que sea, 5 años? Esa es una. Y la otra pregunta era más científica, era del último que sacaste del centro de la galaxia, ¿son de las mismas estrellas con las que están tomando la determinación de... ¿Es el mismo campo?
Es el mismo campo.
Es el mismo campo, pero digamos, la escala es que se pierde la escala. Por supuesto que es el mismo campo porque estás alrededor del centro de la galaxia, del hoyo negro, pero ¿qué tanto se parece a las imágenes esas que tenemos donde vemos que las estrellas se están moviendo en tiempos cortos?
Sí, no, es...
¿Sabes de qué estoy hablando,
sí.
verdad? Sí. Okay.
Es... ¿De qué? No, primero, Para el VLTI, de tiempo de observación con los ATs, es el 80% de las noches más o menos. El otro 20% se pierde entre técnico o el hecho de que es necesario mover los telescopios de una estación a la otra, ¿no? Entonces, ahí es más o menos un par de noches por cada movimiento por cada reconfiguración. Para los UTs es más o menos un 20%. Ahora mismo es un 20% porque particularmente por el centro galáctico, porque se ha vuelto muy, o sea, es un proyecto bastante gordo, es muy importante. Por ejemplo, les cuento, al mes se hacen 10 noches más o menos con el VLTI, de las cuales 5 van al centro galáctico. Algo así. Entonces, particularmente por eso creo que ha recibido más tiempo. Pero la idea, como les digo, es todavía abrirlo más a la comunidad, o al menos mi idea sería abrirlo más a la comunidad, porque sigue siendo una comunidad muy pequeña y hasta ahora o sea, la gente que hace propuestas para tiempo de VLTI es exactamente la misma de los últimos 20 años, ¿no? No es muy abierto y tampoco se conoce mucho qué se puede hacer. Entonces, esa es una cosa. La otra, para este caso, las estrellas, Sagitario está más o menos aquí. Y las estrellas que están observando del centro galáctico es un cuadrito aquí. O sea, si esto es 5 arcseconds, es, no sé, mucho menos de un arsecond. La escala son 260 miliarseconds, algo así, con los ATs. Y con los UTs, la escala para la S2-star es 60 miliarseconds. O sea, el field of view. Es claro que ahora mismo la separación es súper pequeñita, ¿no? Por el periastro. Pero hay muchas de estas estrellas en las que incluso en este tipo de observaciones se pueden ver sus movimientos. Por ejemplo, de hecho, nosotros vemos los movimientos de estrellas que están embebidas en este brazo, ¿no? Exacto. Sí. O sea, lo que vemos son, bueno, los proper motions. Y para las estrellas que no están tan embebidas, que tienen líneas y que se puede tener también la velocidad radial, pues se puede calcular la órbita en 3D, ¿no? De hecho, estas observaciones de aquí, tomadas con NACO, son las que se han usado por los últimos 13 años, 16 años, para monitorear los movimientos del S-Cluster, que es este complejo de estrellas que está más o menos aquí, que es la simulación esta de las estrellas moviéndose.
Dijiste que es múltiple. ¿Qué multiplicidad le encuentras? IRS-13.
Esto es bien extraño. No sabemos exactamente si es un pequeño clúster y no se sabe exactamente si son objetos puntuales o cada uno de estos es binario. O sea, de hecho, esta sería una de un posible caso de estudio, finalmente. Pero lo interesante de esta técnica, o lo que a mí me llama la atención del Aperture Masking, es que al usar simplemente este filtro, tú te quedas sin toda esta emisión difusa que muchas veces te estorba para hacer las medidas fotométricas o incluso la astrometría. Y, por ejemplo, para este tipo de observaciones, tú no pierdes la astrometría absoluta, ¿no? Porque tú puedes calcular exactamente, tú tienes estrellas de referencia que tienen máseres, entonces tú puedes tener un sistema de referencia preciso y no pierdes la astrometría absoluta. Cuando tú utilizas el VLTI, tú pierdes la astrometría absoluta, por decirlo de alguna manera. Solo tienes la astrometría relativa entre la binaria o el sistema triple que tú estés observando en el campo de visión de los telescopios. Pero aquí tú no pierdes eso. Y ganas un factor 2 en resolución, más el quitarte toda la emisión difusa que tienes ahí.
¿Más preguntas?
Oye, si le cambias la máscara, entonces puedes desentrañar este problema digamos, de qué tipo de multiplicidad tuvieras ahí.
Sí, o sea,
porque la máscara que pusiste no sé si es random.
Hay dos. Bueno, primero, las máscaras, el diseño de las máscaras no es también otro tema, porque las líneas de base tienen que ser no redundantes. Entonces, ese es un punto, para obviamente muestrear diferentes frecuencias espaciales. Esa es una idea. Aquí puedes usar la máscara que tú quieras y analizar las imágenes simplemente haciendo una deconvolución de la máscara, ¿no? Porque tú tienes la geometría de la máscara, entonces sabes cómo se forma el patrón de interferencia de manera precisa. Puedes quitar esto y te quedas con este tipo de imágenes aquí. La otra manera de analizar este tipo de observaciones es interferograma por interferograma. O sea, tú tienes el patrón de interferencia y puedes recuperar visibilidades y fases de ese patrón de interferencia y recobrar la distribución de brillo de esas estrellas, que es el caso que nosotros seguimos para recobrar los Bauschocks, ¿no? Entonces, si tienes una binaria y quieres como la medición precisa, yo iría al espacio de Fourier y analizaría los datos en Fourier y trataría de hacer un fitting de un coseno para ver la separación y la diferencia en brillo de las componentes, etc.
Ok, ¿más preguntas? ¿Comentarios? Si no, vamos a darle las gracias de nuevo a Rafael.
No sé cuánto tengo más tarde. Sí, gracias. Hola.